In the next 1 hour and 50 minutes, I would like to share with you what I learned about cold package optics. This lecture is sponsored by IEEE EPS. EPS, by the way, my email is there. You have the presentation file, do you? No. Where is organized? Yeah. You can send them the presentation file. You have any question, email me, I will respond. Okay, so this is sponsored by EPS. Please read it. This is the content of my talk. Silicon photonic. You used this terminology before, did you? Yeah. Many of my friends, they like to talk about silicon photonic. And they even say they are working on silicon photonic. But they don't even have a fact. They say they are working on silicon. Silicon photonic is the integration of IC and photonic on a silicon wafer. So, silicon photonic is for silicon integrations. So, on a wafer, you integrate the IC and the photonic by CMOS technology. It is very difficult. In the whole wide world, the only company who is in high volume production on silicon photonic is only Intel. TSMC 10 years ago, they made the announcement, we will not work on silicon photonic. So, from now on, they use the terminology silicon photonic. Yeah. That is silicon photonic. On a piece of wafer, you integrate the IC and photonics by CMOS. Today, I will only talk about cold package optics, which is by packaging method to integrate the photonic IC and the electronic IC on the same substrate. I am not a semiconductor people. I am a packaging people. So, cold package optics is heterogeneous integration of the PIC and EIC on a single substrate. We call that cold package substrate. Everybody got it? Okay? I cannot talk about silicon photonic. If you are looking for silicon photonic, this is not for you. I am talking by packaging method to integrate the photonic IC and the electronic IC. That is all. Okay? Got it? So, what is the advantage of called CPO. There are at least 3 advantages. One, this is a LED, so laser doesn't work. One is to increase the electrical performance, to reduce the power, to enhance the electrical performance. Okay. So, very clear. I will only talk about heterogeneous integration of photonic IC and electrical IC. Also, what I'm talking about is not for mobile device like a smartphone, because what I'm talking about is too much for them. Okay, it is not application for those mobile devices. What I'm talking is about data center, high performance computing products driven by artificial intelligence. So today, the data center is on your left. You have the switch, you have all the pluggable transceiver. 90% today, the data center, those transceivers are pluggable. However, in the future, on your right-hand side, it will be co-packaged optics. It will have a switch with 16 optical engines. Those optical engines will have the PIC, such as the driver, TIA, the laser and the photo detectors, and the EIC, such as laser driver and the TIA. I make up this to share with you what the industry is doing. First one is pluggable. That means the switch with a substrate on the center of the substrate. On the 4 sides of the substrate, you will have the pluggable transceiver. That's what we are doing today. 95% data center is in this technology. 6 years ago, people say, why don't you try on-board optics? On-board optics is to move the transceiver from the edge of the substrate to 4 sides of the ASIC strip. Oh, this is a big improvement. The signal delay is reduced. So, by moving the pluggable transceiver from the edge to the interior of the board around the edge of the ASIC substrate, it's a big improvement. We call it on-board optics, OBO. About 5 years ago, people say, let's do a little bit better, which is near package optic, NPO, which is to use a substrate to support the ASIC strip and the optical engine. That is a step improvement from OBO. Of course, the industry want on co-packaged optic, which is to move all the optical engine side by side with the ASIC switch on the same substrate. This is what we call co-packaged substrate. On the same substrate, you have the ASIC switch. Right next to it, you have the optical engine. This is called co-packaged optic. Today, only Intel and Broadcom, they are doing it. Oh, by the way, this is our pattern. Okay, so it shows you the ASIC switch side by side with the electronic IC and the photonic IC. They are on a organic interposer, and then on the package substrate, and then on the PC board. Okay, so this is whole package optics. How to make the organic interposer? I mean this. How to make the organic interposer? There are two ways to make it. One, by the way, there are two ways to make it. For both ways, you have to make the package substrate and the organic interposer separate. After that, there are two ways to go. One is to assemble the organic interposer on the built-up substrate to make sure it is a good hybrid substrate. And then you found the ASIC switch, CP, PIC, and BIC. That's one way. The other way most of the people do is after you make the organic interposer and build up substrate, you find the switch PIC, EIC on the organic interposer first, and then assembly on the build-up substrate. So there are two ways to do it. Okay, I prefer the first way. You make the organic interposer. You make the build-up substrate. You find the organic interposer in the build-up substrate, and then test it. Make sure it is a good hybrid substrate. And then you found the switch, you found the PIC, you found the EIC. I prefer this way. And my company can do it very well. By the way, my company is a PC shop. We make PC board. Okay? So we can make the build-up substrate, we can make the organic interposer. We bind it together and test it. Make sure it is a good hybrid substrate, and then we ship it. The OSAC just pick up the ASIC switch and bound on the hybrid substrate. PIC bound on it. PIC bound on it. That's it. Okay, so that's why I prefer the to bound the organic interposer on the build-up package substrate first and test it and make sure it is a good hybrid substrate and ship it to the OSAC. So one is make the organic interposer, bound the chip, and then do the assembly. Another one, the one I like, which is to combine the organic interposer on the build-up substrate. Make sure it is a good one, and then ship it to the OSAC, and then OSAC bound the switch, PIC, EIC on the known good hybrid substrate. I'm going to skip some of this. Please read it yourself. If you have some questions, please ask me. This is our applications. Okay. So please read it. Okay. Intel, they ship their product, which is the ASIC is on the center, and then you have 16 optical engines. Okay. Broadcom also ship their co-packaged optics. Okay. Again, you have the switch, and then you have 16 optical engines. Everything is fine. That is for 25.6 terabits per second. But next generation is 51 terabits per second. But the form factor is the same. So the package of the industry faces a problem because the optical engine, the size will be increased. Those 16 optical engines around the switch, the size increase. But the substrate size is the same. So what can we do? Well, one way is to stack up the PIC and EIC. And you can place the optical engine on the substrate. For example, we stack up the EIC on top of the PIC with organic interposer. So in this case, the substrate can support. Everybody got an idea? That's why I call it 3D heterogeneous integration of PIC and EIC. Okay? Yeah, this is some of our technique. So this is what I give you today. How to set up the PIC on the EIC so you can put it on the same substrate. That means you increase in the vertical space, but you still can keep the horizontal space the same. Okay? So these are the 11 different 3D heterogeneous integration of PIC and EIC. Okay. So I go through it one by one with you. This word. Okay. Oh, this doesn't work. The first one is to stack up the EIC on the PIC by microbump. And then the signal is coming out from the Y band on the PIC to the next level of interconnect. And the signal is coming in from the fiber to the PIC. This is first one. The second one, the signal is coming from a fiber to the PIC, and then the PIC is connected to the EIC with the microbump. And the signal is coming out from the C4 bump to the next level of interconnect. The third case is very popular in research lab today. The third one is to stack up the EIC on the PIC, and the signal coming in from the fiber to the PIC. And the EIC and PIC is interconnected with microbump, so-called C2 bump, also called copper with solder cap bump. Okay. And then the EIC is with TSV through silicon via. And then microbump to the next level of interconnect. The fourth case is EIC attached to PIC, but not with microbump. Is with copper to copper hybrid bump. The fifth case is the EIC attached to the PIC through a PS3 interposer. Case F, the EIC is connected to PIC. We replace the TS3 interposer to organic interposer. Case G, the signal coming from the fiber to the PIC, and then microbump on the TSV interposer, and then microbump to EIC. And the signal is coming from the microbump to the next level of interconnect. Case A is basically the same, except I replace the TF3 interposer to organic interposer. Case 9 is basically the same, except I replace the microbump into copper to copper hybrid bonding. Case 10 is the signal coming from the fiber to PIC and then microbump on a substrate, and then the EIC is with solder bump on the package substrate. So this is package on package. Case 11 also is package on package, except the EIC is not on the package substrate. The EIC is fan-out embedded with epoxy molding compound. So I give you 11 different cases to stack up the PIC with EIC. With C4 bump, C2 bump, which is micro bump, and copper to copper hybrid bumping, plus TSV through silicon via interposer. Okay, so I encourage you to look at this and then think maybe there are some other packaging structures. Think hard. There will be others. Apply for a patent. Bear with your name. No, I'm serious. Okay? I give you 11 days. You can think harder. Different packaging structure. Okay. So, because my proposal here involves C4 bump, C2 bump, TSV, and copper to copper hybrid bonding. So each one I will very simply mention to you. Oh, by the way, before that, this is Cisco's paper. This is our case 3. The EIC is on top of the PIC with micro bump, and then with TSV on the substrate. This is our case 3. This is by Spill, published a few months ago. They use fan-out to embed the application processor in the EIC. So this is our case 10. Okay. So people are using it. Okay. I'm very happy. As I said, all this stacking up 3D needs C4 bump, C2 bump, TSV, and copper to copper hybrid bumping. So, this is how I feel the trend on C4 bump, the solder bump, and the copper material with solder cap, the micro bump. Today, most of the people use C4 bump is 100-meter diameter, 150 micron pitch. Some people using 50 micron diameter solder bump and 100 micron pitch. In laboratory, some people doing study by using 25 micron solder bump and 50 micron pitch. On the copper pillar, so-called the C2 bump, today, most of the people use 50 micron copper pillar and 100 micron pitch with solder cap. Some people are using 25 micron diameter copper pillar and 50 micron pitch. Some laboratory, they are doing research with 10 micron copper pillar with 20 micron pitch. Smaller than that. No solder cap, just bare copper and bound to another bare copper, so-called copper hybrid bonding. Anyone here working on copper, of course, not in production, I know, but anyone here working on copper with copper hybrid bonding? Anyone?
Not in
Huh?
not in atoms.
No, but I tell you, it's coming. Why is coming? You know, there is a conference called ECTC. Everybody know? That is the direction for packaging. The best packaging conference on earth every year in May. You know, last year, the whole conference, how many papers on copper to copper hybrid bonding? How many? You want to guess? Wow. How many? How many papers? Huh? 100? No, not that many. 82. A whole conference. 82. Nothing else but copper to copper hybrid bonding. The year before, how many papers? 78. In the year before, 72. Now, this year, I don't know how many. I have to wait until May 26. Okay? So I'm looking forward to it. This is how to do wafer bumping. Please read it yourself. Okay? This is the hybrid bump. Okay? Please read it yourself. If you have questions, please email me. Okay? Everyone, in packaging, you heard about a terminology called bridges. Yeah. You? Huh?
Silicon bridge.
Yeah, silicon bridge. Very good. Who else? You?
Even.
Yes. Who else? Now, bridge is a very, very important technology for chiplets and heterogeneous integration. bridges is a tiny piece of silicon, no device, only RDL and TSV, connecting two different chiplets. That's why it's so important. As you know, chiplet is the game today. And the way to connect the chiplet is bridges. And today, most of the bridges, as a matter of fact, all the bridges use microbump. For example, Intel's, EMIB, IBM's, everybody, they use microbump to connect the bridges. This is our pattern. We use butlets, copper to copper hybrid bonding, connecting the silicon bridge and the chiplet. No bump, no micro bump. Two weeks ago, according to the industry news, the computer, their notebook, M5 has been using bridges with microbump. 2 weeks ago, they made the announcement. Their bridges will be using TSMC's SOIC. Now, SOIC is the core and butter of TSMC's technology. SOIC, simply speaking, is copper-to-copper hybrid bonding. So before end of this year, when you open up Apple computers notebook, their M5 connected to M5 with the bridge will be copper-to-copper hybrid. Let's see. How to make a TSV? Of course, it takes all day to talk about it. So I simply show you this one. So please read it. If you have any question, please email me. Yeah, this is how to make a TSV, how to make the redistribution layer on top of the TSV. This is the paper we published 13 years ago. Okay. So please read this. All these are necessary for those 11 cases I mentioned. Okay. These are the enabling technology. Okay. Now I set up the PIC on EIC Ethernet. Okay. So this is not called whole package optics yet. Wait until I set them up and then put it side by side with the ASIC switch on the same substrate. Then we call it whole package optic substrate. Okay, so now I have many cases. The first one is the stack up of the EIC on PIC side by side with the switch on the cold package substrate. Okay, or the cold package substrate can be TSV interposer or organic interposing. I make some proposal. When I put the switch and the 3D PIC, EIC on the substrate, I can use the bridges to enhance the performance. For example, I can use a silicon bridge connecting the PIC with the ASIC switch. Or I can use Intel's EMIB embedded in the package substrate, connecting the PIC and EIC. Or I can embed the silicon bridge in the fan-out epoxy molding compound with redistribution layer. You can use many videos as long as the switch and the PIC and EIC, they are side by side on a single substrate. By the way, this is the definition of heterogeneous integration. You see? Huh? The definition of heterogeneous integration is to have different chips on the same substrate. I have my taxi waiting for me at 1:15 hours. This example, okay, finally is, this is for a product driven by artificial intelligence. You have the graphic processor supporting by the high bandwidth memory. And then on the substrate, you have the optical engine. It's not in production yet, okay? This is my imagination. But it will happen. Okay, so on the co-packaged substrate, you have the GPU, you have the high bandwidth memory, and you have the optical engine connecting the fiber to the outside world. So I make it more complicated so we can apply more patterns. So the GPU is connecting with the switch with the optical engine. So on your right-hand side, this is what we have been talking about. On your left-hand side is for the GPU applies to the product driven by artificial intelligence. They can combine with the fiber and work together. I think 3 to 5 years, if you have. Of course, maybe I cannot wait. I'm maybe 18 years. So this is our proposal. And then all these components are on the co-packaged substrate, and then on the build-up package substrate, and then on PCB. Okay. Glass substrate. Everybody got excited when Intel made the announcement on September 18, 2023. Everybody know that? No? Yeah. Some of you know. Suddenly, everybody is crazy about glass substrate. Last year, I went to China to lecture. I find out there are more than 100 companies working on that. They did not read the last paragraph of the announcement. This is Intel's announcement about the use. Oh, this is the last sentence. Their glass is for 1 trillion transistor on the process. My friend, do you know what is 1 trillion transistor means? No. Your iPhone. I don't have a phone. I never use a phone. But my daughter's iPhone last October. You know how many transistors are there?
20.
20 billion? Yeah, 20 billion. This is 1 trillion. So, glass substrate is for very niche applications. Last year, I went to China. Wow, many people come to me. There are more than 100 companies. They are doing nothing but glass. I'm wondering what's their application. So glass is for niche application. This is their panel. The size is 510 by 515. Oh, this is the panel size of our company. We have a manufacturing line. We can make the organic interposer down to 2 micron line width and spacing. I need 2 micron line width and spacing by PC board technology. We have a manufacturing line, 7 years. We also have a glass. No custom yet. The panel size, the same, 510 by 550. So, for their 1 trillion transistor, they say to replace the organic core into glass core. There are many advantages. Please read it. So, we are also under pressure. Glass. But we know glass is for niche application. And we also know the advantage, higher ability to seamless integrate optical interconnect. So our attention is only applied to optical, the glass substrate. So this is our first application. To integrate the EIC on PIC with a glass interposer. The glass interposer is with TGV. through glass via. So we applied patent for this 2 years ago. No, that's not 2 years, 1.5 years ago. After September 18, 2023. So we set up the EIC on PIC with a glass interposer. We apply another pattern, which is to embed the PIC in a glass substrate. Why we do that? Because on the glass substrate surface, we can make the glass waveguide, which is connecting to the signal coming from outside the fibers. That's why we use glass to make the glass waveguide. One end is connecting to the photonic IC, the other end is connecting to the fiber. Yeah, this is our pattern. And the EIC on the PIC is with copper to copper. This one is with C2 bond. Next one is with copper to copper hybrid bonding. So this is how we see the glass substrate come into picture. Okay. Detail is for 1 trillion application process. We are using the glass substrate for whole package of this. Okay. These are how to make it this real. Of course, there are also challenges. This is the last thing I'm going to give it to you. Of course, today, no one talk about the reliability because of the glass substrate. Okay, no one. So we publish a paper to tell you because of the glass substrate, there is a problem with what the industry is doing. Okay, on your right-hand side, on your right-hand side, you have the conventional substrate, which is with organic coil, built up and then supporting the chip. This is what we have been doing for 30 years. So on the right-hand side, this is what we have been doing for the past 30 years. 1.5 years ago, Intel proposed to replace the organic core with the glass core for their application process. Now, this is the key. the gas core, the CTE is very low because the people make the CTE of gas as close as to the silicon. Because chips is not hot. So they make the CTE of the gas cores as close as to the silicon. Silicon is 2.5. They make it into 4.8. And the organic core we use today is about 10. Also, please know the chip, the fifth chip on the substrate, always with underfill. Is that right?
Yes.
But the solder bump on PC board. So we have two kinds of bump. One is the micro bump supporting the chip. One is C4 bump on the PC board. The C4 bump, we also call it BGA solder board on PC board. No underfill. Is that right? Because underfill is not reworkable. On the large PC board, if something wrong with the chip, the whole thing needs to take out. But if you use underfill for the C4 bump, you cannot remove. The whole board has to throw away. But the under bump under the chip, use underfill. If the chip is dead, just reflow the whole thing. That means the C4 four-way array. Reflow it and throw it. The whole board you still can use. So, what I'm going to show is because the CTE of the gas substrate is closer to the CTE of the chip, the micro solder bump is okay, because it has the underfill protection. However, the thermal expansion mismatch between the glass substrate and the PC board increase. Is that right? Because all the people, when they select the CTE of glass, they want to use it as close to the silicon chip as possible, to make it as small as possible. Then the thermal expansion mismatch between the PC board and the glass is large. Then the solder joint, the C4 bond, but the solder joint is in question because of the large thermal expansion mismatch. That's why I wrote this paper telling the whole wide world the industry is heading into the wrong direction. They should increase the CTE of the glass substrate. Because there is underfill protection, the micro bump should be okay. But the thermal expansion mismatch between the glass and the PC board will be reduced. Then the stress and strain in the C4 bond solder joint will be reliable. Everybody got it? So this really, I'm not going to do it here. You may feel bored about this. Okay. I have 10 minutes left. I will let you ask me questions. I'm going to skip all this. Please, Ricky, if you have any questions, please email me. I propose some R&D project. The first one is I propose 11 there. There must be more. Use your imagination to create more and apply for a patent. On the glass substrate, again, use your imagination to discover some of the structure effectively use the glass substrate. I talk about different setup, PIC, EIC, or EIC, EIC. I did not talk about a very, very, very important problem when you set up the IC, which is how to take it out before it affects the electrical and photonic quality. How to take the heat out. This is a very, very big problem. Very, very good opportunity for us to do thermal management of 3D integration of PIC and EIC. I truly mean, okay, even though I did not know, but it is a very, very important problem. The other reason I did not know is because I did not work. And in the literature, there is nothing on the whole package model. Okay. So it is your opportunity. There are many interconnects. Micro bump, the C4 bump, the PA bump. So solder joint reliability is a big problem. Okay. It's a good opportunity. These are some of my recent publications. By the way, if you are an ETS member, you can download it for free as much as you like. Okay? These are my books. Now, I have 10 minutes left. Please ask questions. Yes. Was it?
Good.
What? Class. What? All kinds of class.
Did you mention?
Yeah.
Your BG, you know, I think, political business. So that this is the transition between. How many of us possible? We actually the could actually based on the something
I guess just by polymers is not enough because the thickness of polymer is very thin. So just by it is not enough. So the glass substrate is about 800. The polymer is only maybe 500. Next question. Yes. How to do optical coupling is out of scope of my lecture today. It itself is big. I don't think it's not important. It is very, very important. But it's out of the scope of my lecture today. Okay. That's all.
We use glasses or Intel they anyone use like 2 different layer of glasses.
2 different layers of glass.
Yeah.
No, I never heard of it. But it's possible. That's what I mean. Use your imagination. Yeah, I never. 2 layers of glass. So, yeah. Oh, I tell you, glass is very high. Oh, oh, here is so you make the cavity. You put the die attach in a B stage, and then you put the PIC, and then make it flat. You know, you have the die attach at B stage, and then you can test it and make it the PIC in the glass flat. Yes. Next question. No? Okay. Thank you very much.